Okay guys, we'll be doing 2.6, continuous with piecewise functions. Okay, let's first start off by just reminding ourselves what the rules are to make a function continuous. Okay, let me get my pen ready here. Okay, I didn't mean to do that, but just ignore it. Okay, write the 3 rules that make a function continuous. Okay, the first one, the limit as x approaches some value, and we're going to call that value c, of our function f of x is equal to, it exists, just that it exists. It's equal to some constant, some number. Okay, then we also need to know that the point of the function exists. And the last thing is that the limit and the point are both equal to each other, so that the limit of the function is equal to the point. Okay, and just an idea of that, a limit would be something that the left and the right both approach. Right now this is not continuous because there's a hole. The point needs to exist and it needs to be at the same place as the limit. That's the only way to fill in this gap, is that there is a point and it's the same as the limit. That'll fill in that gap and it'll make it continuous. If you don't fill in that gap, you just do something like this, and you just put a point somewhere, well, it's not continuous. Like there's a limit here, there's a point here, but they're not equal, so it's not continuous because there's a gap there. It's still not possible to draw this graph without taking your pencil off the paper. And that would answer your the next question here. Draw a function that is continuous and one that is not continuous. Okay, let's go forward. Okay, are these functions continuous at all points? Okay, so remember, in order to do this, first ask yourself what makes a function not continuous. So discontinuous, right? And remember, there are 3 discontinuous things. 1, there's a hole. That's a removable discontinuity. 2, there's a vertical asymptote. Remember, that's an infinite discontinuity. And 3, there's a jump. And remember, you only see these jump discontinuities on piecewise functions. So noticing that none of these are piecewise functions, we're not going to run into this discontinuity. So just look here and see if there's a hole or vertical asymptote on any of these. And
teachers, pardon this interruption. At this time, please put your breakfast coolers and...
Okay, so we're just going to be looking for holes and vertical asymptotes on any of these. And if they have them, then that would make it not continuous. If they don't have them, then that would make it continuous. Okay, so this first one. Remember, holes and vertical asymptotes occur when you divide by 0. Since there is no denominator here, there's no hole or vertical asymptote, so that is continuous. And if you looked at a graph of that, it's a negative x squared. It would look something similar to this, yeah? And that is continuous everywhere. Okay, this one, now it doesn't have a hole or vertical asymptote, but I'm asking if it's continuous for all points. And if you know what a graph of a parent function, a parabola looks like, or a square root, it looks something like this. And you have no negative values. So there's no function over here, no function over here. So since there's no function over here, there's no x values, you can't say it's continuous for all points because it doesn't have all points. So here we're going to say not continuous. And if you want to write a reason, we can just say because there are no negative values, x values, yeah. Okay, there are no negative x values. Okay, over here, is there discontinuity? Yes, there's definitely discontinuity. When you plug in -3 here, you divide by 0. So it is not continuous. And if you were to factor and cancel, you'd see because there's a hole. And it's not continuous at x equals -3. That's the only place it's not continuous. Everywhere else it is. Okay, this one. This one is also not continuous because you can divide by 0. And where is it that it's not continuous? It's at x equals, what would make it divide by 0? 2. That's where it's not continuous. Everywhere else it is. Okay, a cube root. If you know what a cube root looks like, the parent function of a cube root is going to look something like this. So you can have negative values. It's not like a square root. If you have an odd number here, an odd number, then it is continuous for all numbers because you can have negatives. Okay, this last one, e to the x. Do you think that's continuous? First, think about the graph. The graph looks like that. It crosses right here at 1. At 0, it hits the y value of 1. Okay, well, we have all negative and positive x values. So yes, that's continuous. Now, some people might say, but you don't have negative values. But remember, we don't care about the y values. We just care about, does it cover all x values? And in this case, this function does cover all x values. Okay. Okay, so what we're going to be doing today is checking if these piecewise functions are continuous or not. And if it breaks any rules, tell me which one. So you guys have already done these before with limits and points, so it should be pretty easy. Step 1. Does it have a limit as x approaches, and we're going to be checking at the transition value here, -1 of our function y. Okay, so remember, for a limit, we need to check the left and the right. In this case, this is the left, this is the function for the left, this is the function for the right. Okay, let's plug in -1 and see if they're the same thing. From the left, -3, -1 squared minus 1 plus 2. That's going to be 1, -3 minus 1, -4 plus 2 is going to be -2. Okay, let's plug it into the right. 2 times -1, that's going to be -2. Okay, so the limit does exist. It's -2. Okay, second step. Is there an f of -1? Well, let's see here. Here's the equal sign. That's going to tell me this is the function we use for equals to, and I already did that work, so I'm not going to redo it. It's -2. Okay, so it does have a point. It does have a point, and it does have a limit. Are they the same? Yeah, they are. So the limit as x approaches -1 of y is equal to f of -1. So we're good. It's continuous. Sweet. It meets all three things. Okay, let's check this one. Okay, first step. The limit as x approaches, we're checking 1 here, not -1, but 1 of our function g of x. Okay. Let's plug in, now if you notice, this is the one that we're going to use from the left, this is the one we're going to use from the right, because we're doing limits, right? Okay, left, right. Let's plug in 1, we get 4, 1 squared, which is equal to 4. Okay, now we're going to plug it into here. -1 plus 2, which is equal to 1. Well, they don't approach the same place from the left and the right, so the limit does not exist. So therefore, not continuous. Cool. There's an example of continuous. Here's an example of not continuous. I got a couple other ones that maybe are more difficult, so let's look into it. There's graphs of them. If you notice on this one over here, it was continuous. Notice how there's no break. You can draw it without taking your pencil off the paper. Notice on this one there is a jump because there was no limit. We said that. From the left it was approaching 4, a y value of 4. From the right it was approaching a y value of 1. So we have a does not exist on the limit. Okay, find out if this function is continuous or not. Okay, let's do this. Start at step 1. Okay, the limit as x approaches, -2. G of x. Okay, we're going to check from the left and the right. Looks like this function is from the left. This function is from the right. Okay, left and right. Okay, 2 raised to the -2 plus 1 over 2 times -2. That's going to leave me with, remember, the negative exponent means that it really belongs on bottom, so it's 2 squared plus 1 over -4. Okay, now let's rewrite this. We got 1 over 4, that's this, 1 over 4, minus, I can move that negative so it's here, 1 over 4. Okay, so that means from the left it's approaching 0. Let's see where it's approaching from the right. We're going to plug in 2, -2, I'm sorry. -2 plus 2 is 0 over negative 2 squared, not plus, minus 10. That's going to give us 0 over, this doesn't really matter as long as it's not 0. 4 minus 10 is going to be negative 6, which negative 6, 0 divided by negative 6 is 0. So it looks like we do have a limit. It's at 0. Okay, check number 2. F of negative 2 equals, okay. Well, we don't have an equal sign on either one of these. So that means that there's no point. It doesn't exist. So therefore it's not continuous. Now what I would have done here from the start is I would have noticed that this does not have an equals to sign on either one of these. And I would have just skipped to step 2 and said, hey, look, there's no point. That means it's not continuous. I wouldn't have even dealt with any of this limit work. Because why deal with the limit work if you already know it's not going to be continuous because there's no point. Okay, I got one more for y'all. Okay, here we go. Start with first step. Limit as x approaches. It looks like we're checking it at the transition value, which is 2 of our function g of x. Okay, remember we're checking from the left and the right, correct? Okay, notice this is equals to, and this is does not equals to. If you remember these, this one right here checks both the left and the right. I love it when it's like this because all we do is we just have to plug it into one equation instead of both. So let's just plug in 2 to the top equation. So we got 2 squared minus 4 all over 2 minus 2, which looks like 0 over 0. Okay, first step didn't work. Remember, you go on to the next step. Let's factor and cancel it. So we got x plus 2, x minus 2, all over x minus 2. Okay, we do have a hole, a removable discontinuity. We get rid of it. We have a brand new function. Ignore that function. We're never going to use that function again. So I got this new function, x plus 2. That looks exactly like that other one, but there's no holes in it because we removed the hole. Hence, removable discontinuity. Okay, well, let's check our limit with this. 2 plus 2 is 4. Yeah, we got a limit. It's 4. Okay, let's do step 2. F of 2. Remember, that's where it's equals to. That means we're going to be using this function, the top function. Okay, we're going to plug in 2, so that's 4 times 2. That is 8. Well, it looks like we do have a point, we do have a limit, but they're not equal to each other. So step 3 fails. Let's write it down. The limit as x approaches 2 of our function g of x does not equal f of 2. Therefore, not continuous. Okay, that's it. Oh, sorry. There is a little bit more. So, how could you make it continuous? Well, I can make it continuous by making the limit and the point equal each other. So, to make them equal to each other, how about we just get rid of this x? Oh, let me go back to this. If you get rid of that x, that makes the point f of 2 equal to 4, just like the limit as x approaches 2 of our g of x function was equal to 4. And then that would make it continuous by just switching this function from 4x to just 4. So how could you make it continuous? By making x equals 2 to be just 4. Yeah? And that's it.